right, section 13.8 is Stokes' theorem. And I'm going to write Stokes' theorem for you right now. Integral over C, which would be a line integral, okay, or curve, f dot dr, okay, is the same as the integral over a surface of the curl of f dot ds. Okay, where f is a vector field, and C is the boundary of a surface S. Okay, basically it's like Green's theorem, but S isn't flat. Isn't flat. So remember in Green's theorem we had like D, C, okay, and D was this flat surface. S isn't necessarily flat. S can be kind of can be a curve that's kind of changing in the Z direction. Okay. So let's get a little bit more here, a little bit more of the background again. Okay. So back up to Green's theorem. The integral over C P dx plus Q dy. And remember that was f dot dr, okay, where f was pq, dr would be dx dy, basically. Okay, so that's your dot product, right? Is the integral over d of dq dx minus dp dy dA. Okay, this relates a double integral over a plane region D, and plane means flat, right, to a line integral around its boundary C. Okay. Then we've got Stokes' theorem, which starts out very similar. Integral over C of f dot dr equals integral over S of the curl of f dot ds. Okay. And this relates a surface integral over a surface S, okay, not plane, right, not a planar region, a surface, to a line integral around its boundary C. Okay, and it does require positive orientation of the surface. Otherwise, we would just make it negative. Okay. And I'm going to go back to that from section 13.7 that we just did. If we do the integral over S of f dot ds, okay, that's the integral over d of negative p dg dx minus q dg dy plus r. That's a q. dA. Okay. So we can use something similar where once we have the curl of F, we can take that P, Q, and R, okay, and do something very similar. The surface translates to be the same thing, okay? So we'll use that, what we learned in 13.7. Again, I don't want to say this is not equal to this, okay, because it's the curl of F that we're going to use to get the P, the Q, and the R from, okay? So get P, Q, and R from the curl of F and use that same relationship there. Okay. So Green's theorem is Stokes' theorem, but just with a flat surface. Okay. And again, we could do a proof for that, but we're just going to leave it for now. Okay. All right. So we're going to do we're going to jump right into the examples already. Okay. So the first example, I believe this is exercise 2 in your book. Okay. They give you that f of x, y, z is 2 equals 2y cosine zi plus e to the x sine zj plus x e to the y k. Okay, and S is the hemisphere. X squared plus y squared plus z squared equals 9. Okay, we know that's a sphere with a radius of 3. Hemisphere, we'll just do the top half, and they're going to give us that it's oriented up. Okay, so, and it says use Stokes' theorem to find this. Okay, and more typically use Stokes' theorem the other way. Okay, so they're saying find this by doing this. Okay, it's more often that we would find this by doing this. Okay, but they want us to do it this way first, so we're gonna do it this way first. Okay, so we have, first of all, we have to get R. Okay, whenever we're talking about this, R, okay, is some function. X, Y, Z. Okay. And we're talking about the surface here. So we're talking about this hemisphere with a radius of 3. I should do that as dash line in the back, but anyways. Okay. So, and also when we're talking about this, we want the projection of the surface onto the XY plane. Okay. So R would be 3 cosine t, 3 sine t, 0. Okay, so we're not looking at the boundary of the surface. We're looking at the surface as if it were projected on the xy plane. Okay, and this is for t is between 0 and 2 pi. Okay, actually, scratch that. It is the boundary, right? Because it's not t is between 0 and 2 pi. The radius is always 3. Okay, we're looking right there. I was thinking I was jumping ahead to this guy, which is not what we're doing. We are finding this integral. Okay, so we're only looking around the boundary. Okay. All right, so that's your parametric equation for the boundary. Okay, we're doing a line integral here. Okay. So we found the parametric equation of the boundary, and then our dr dt, right, because that's really what you're finding, is, if this is r of t, we're going to have negative 3 sine t, 3 cosine t, 0. Okay, so there's the dr part. Okay, and then f would equal, let's see, 2, we're looking back up to this f here, y, which is 3 sine t, cosine of z, so cosine of 0, okay? And then e to the x, sine z, and then we'll have x, e to the y. Okay, so we're going to have cosine of 0 is 1, sine of 0 is 0. Okay, so we're going to have 6 sine t, 0, and then 3 cosine t times e to the 3 sine t. Okay, all right, so again, dr, where r is the boundary. Okay, so find your parametric equations for the boundary of the surface, and then dr dt, take the derivative of it, and then f is just your function in terms of those parametric equations, and then we got to take the dot product. Okay, so f dot dr would be negative 18 sine squared t plus 0 plus 0. Okay, so we're going to do the integral from t is 0 to 2 pi of negative 18 sine squared t dt. Okay, so negative 18 sine squared would be 1 minus the cosine of 2t over 2 dt. So t minus the sine of 2t over 2 from t equals 0 to t equals 2 pi. Well, if I plug t equals 2 pi into this piece, it'll be 0. If I plug t equals 0 into anything, it'll be 0. So it's just negative 9 times 2 pi, which is negative 18 pi. Okay, so we found a line integral. That's it. Okay, and that line integral by Stokes' theorem is equivalent to that surface integral. Okay, now we're going to do the opposite. Okay, this is exercise number 6 in your book. And we have the vector field. Okay, and then C is the boundary. Okay, and again, in the previous one, they gave you S. Okay, so they gave you the surface. And so then we had to figure out what C was, which was the boundary. Now they're giving us the boundary. Okay. Okay, in octant 1. So that's a plane. It's very hard for us to come up, or it'd be more difficult for us to come up with the parametric equations of that plane. So use Stokes' theorem to find the integral of C f dot dr. Okay, so again, if we wanted to do it like we did in the previous example, we'd have to find the parametric equations for that plane. And then we have to parameterize the function in terms of that. It gets kind of dicey. Okay, so, and they tell us use Stokes' theorem. So that means that instead of doing that, we are going to do the integral over the surface of the curl of f dot ds. Okay. And then we're also going to use that equation from 13.7 that I showed you, where when we're doing the integral over surface of f dot ds, it's the same as the integral over the region, okay, of negative p dq oops, sorry, dg dy minus q dg, I'm going to fix that because it should be dg dx. Okay, plus r dA. Okay, so that's, again, that's your surface. And we switch it to the region. Okay, so we're going to find, and again, instead of using f, it's the curl of f is what we want. Okay, so the first thing we're going to do is find the curl of f, which is del f. So we've got our cross product I, j, k, and then d, dx, d, there's your del operator, dy, d, dz, and then f is 1, x plus y, z, xy minus square root z. Okay, so we find our cross product here. When we do the i's, partial of xy minus square root of z with respect to y would be x minus y. Okay, and then we do our j's. Let me erase that. And we can do it in the opposite order. Okay, so we'll have 0 minus y. And then we do our k's, we'll have 1 minus 0. Okay, so when we use this equation here, this is your P, Q, and R. Okay, all right, and then our surface is 3x plus 2y plus z equals 1. So we can solve that for z. Okay, which is like your g of xy. Okay, so dg dx would be -3, and dg dy would be -2. Okay, so we're going to be doing the integral of -p, so I'm going to do y minus x. Oh, you know what? I should have left it because the other one is -2. The 3 is negative. Okay, so we're going to have 3 times x minus y minus q, so plus 2. Oh, and we got 3 negatives, so it's negative. Gotta be careful with any shortcuts that I'm taking. So it would be, that would still be negative. Okay, and then plus r, so plus 1 dA. Okay, so now we have to figure out the limits of integration. Well, remember, we take that surface in the line integral, in the surface integral, and when we use this equation, we find the region in your xy plane. So let's take a look at that surface. Again, it's 3x plus 2y plus z equals 1. So when x and y are 0, z is 1. When y and z are 0, x is 1/3. And when x and z are 0, y would be 1/2. Okay, so we're looking at that. In your xy plane, you can go to 1/3 here. We're going to go to 1/2 here. Okay, so that slope would be -1/2 over 1/3, which is -3/2. Okay, so that line would be y equals 1/2 minus 3/2 x. Okay, so x is between 0 and 1/3. Y is between 0 and 1/2 minus 3/2 x. Okay, so there's our limits of integration. So 0 to 1/3, 0 to 1/2 minus 3/2 x. I'm going to expand this out. So I'm going to have 3x minus 3y minus 2y, so minus 5y, plus 1. And then we're going to have dy dx. Okay, so it's all set up then. All right. Again, I kind of want to go back and just summarize, right? So we had our vector field, and then we have our surface. Okay, if we want to find this line integral, it's the same as doing this surface integral. Okay, and if we're going to do the dot product of a vector field and a surface vector like that, we can use this equation here. Okay, where P, Q, and R, where this technically is the curl of F. They're both vectors. Okay, so we're just using that idea there. So we find the curl of F first. Okay, that gets you your P, Q, and R. And then our surface in terms of X and Y only. Okay, gets you your G, so you can find the dg and the dg dx and dg dy. And when we use this equation, rather than doing a surface, we do a region. Okay, and then it's all set up. Okay, and I'm going to skip the tedious part of doing the actual integral. But you can check for yourself that you should get 1/24. Okay. All right. Now we're going to do another. We only have one more example to do. This might be a little bit of a shorter video. Okay. We're going to actually verify Stokes' theorem by doing a problem both ways. Okay. So I think this is exercise number 12 in your book. Okay. So our vector field. So sometimes, what we just did, sometimes it's easier to do one side of Stokes' theorem to find the other side. Okay, so like rather than find that line integral, I'm going to do the surface integral, or rather than doing that surface integral, I'm going to do the line integral. We're going to do both now and just show that you get the same answer. Okay, so our vector field, negative 2yz I, okay, plus yj plus 3xk is your vector field. And our surface is the paraboloid. Z equals 5 minus x squared minus y squared. Above, the plane Z equals 1. Oriented, upward. So it's a positive orientation. Okay. All right, so let's draw this paraboloid. Okay, first of all, so we can kind of get the pieces that we need here. So we can see the axis will be in the z direction, right? If x and y are both 0, z is 5. That's your vertex of your paraboloid, right? Since we have the negative x squared and the negative y squared, it opens down. And then we go to when z is 1, when z equals 1, which is the plane, that is the base of this paraboloid, basically, we'd have 1 equals 5 minus x squared minus y squared, or x squared plus y squared equals 4. So we'd have a circle with a radius of 2. Okay, so this is your paraboloid. Okay, and that radius would be, I'm just going to do 2. Okay, so let's be clear here of what all these pieces are. Okay, this whole paraboloid, okay, that is S, your surface. Okay, this piece here is the boundary. Okay, that is C. And then this piece, just a second, I want to make sure that I'm doing it right. Yeah. The projection of that into the xy plane with no bearing on the height. That is D. Okay. So those are those little subscripts on the integrals. That's where they're coming from. Okay. And again, we're going to verify Stokes' theorem. So we're going to verify that the integral, the line integral over that boundary of f dot dr is equal to the surface integral of the curl of f dot ds. Okay. And in doing that, we're going to use that equation with the p and the q and everything in it. Okay. So yeah, we'll get there. I don't want to. So we're going to use, I'm going to put it here, that this would be the integral over d of negative p dg dx minus q dg dy dy y plus r dA. Okay, where P, Q, and R are from curl of F. I just want to make it super clear that those don't come from F, they come from the curl of F. Okay. All right. So again, there's your little subscripts, C, S, and D. And visually on that sketch, you can see what we're talking about there. Again, G is just the surface. Trying to think of what else we need here. I think we're good. Okay. All right. So again, I mean, think about that means that the line integral of that vector field around that boundary C is the same as the surface integral of the curl over the entire surface, which is the same as this kind of expression here. Okay. Which, I mean, really, this is almost like the dot product of the curl of F with the partials of G, with the exception of some positive and negative signs there, right? And that is, I should say with the gradient of G, okay? And that's equivalent to that weird expression over the surface D, okay? And it's kind of crazy how all of those relationships just kind of work out. They're all equivalent, okay? All right, so first of all, let's do the first part there, okay? Our boundary, C, okay, that would be x squared plus y squared equals 4, okay? We want to parameterize it, right? We always parameterize this piece. So x would be 2 cosine theta, y would be 2 sine theta, where theta is between 0 and 2 pi. Okay. Oh, and I forgot that z is 1. Okay. Because that c has a height of 1. Okay. So then your r of t would be 2 cosine theta, 2 sine theta, 1. R prime of t would be negative 2 sine theta, 2 cosine theta. You know what? I said t. I might as well just do theta. Okay. So that's your dr, okay? And then f of r of t, if you go back up, right, our equation for f, I got glitchy there. All these guys, I got to plug in my x, my y, and my z, okay? So that would be, it's negative 2yz, so negative 2 times 2 sine theta. Can't switch between theta and t. 2 sine theta, and then z is 1. Okay, and then the j component in f is y, so 2 sine theta. And then 3x, so 3 times 2 cosine theta. Okay, so that would be negative 4 sine theta, 2 sine theta, and then 6 cosine theta. Okay, so then f dot dr would be 8 sine squared theta plus 4 cosine theta sine theta plus 0. Okay, so we would do then the integral from 0 to 2 pi of 8 sine squared theta plus 4 cosine theta sine theta d theta. Okay, and we're going to split that up into 2 separate integrals. Okay, so we would have 8 integral from 0 to 2 pi, 1 minus cosine 2 theta over 2 d theta. Okay, plus 4 integral from 0 to 2 pi of cosine theta sine theta d theta. And for that, we can do a u sub, where u would be sine theta, du would be cosine theta d theta. So we would have 4 times the integral from 0 to 0 of u du, which is 0. Okay, so that piece becomes 0. Okay. So then all we need to do over here would be 4 theta minus sine 2 theta over 2 from theta equals 0 to theta equals 2 pi. And again, for that second piece there, if I plug in 2 pi or 0, I get 0. So all I really need to worry about is plugging in 2 pi for theta. So that is 8 pi. Okay, so we did our line integral around the boundary. Now we're going to do our second piece here and hope it comes out the same. Okay, our integral over the surface of the curl of f dot ds. Okay, and remember we're going to use that the integral over the region of negative p dg dx minus q dg dy plus r dA, where p, q, and r come from the curl. Okay, so your curl of f is I j k d dx d dy d dz, and then f 2 negative 2yz y and 3x. So our I components give us a 0. Our j components give us a, let's see here, negative 2y minus 3. And our k components here give us a 0 minus a negative 2z, so 2z. Okay, so there's your p, q, and r. Our surface, remember, was already solved for z. G of xy is 5 minus x squared minus y squared. So dg dx would be negative 2x. Dg dy would be negative 2y. Okay, so we've got the integral of negative p dg dx, so that'd be 0. Okay, and then minus q. Okay, so that'd be a positive 2y plus 3 but then dg dy is negative 2y. So we would have negative 2y times 2y plus 3. Okay. And then plus r. Okay. So then we'd have negative 4y squared minus 6y plus 2z dA. Okay. And remember, we're doing this over, oops, not s, over d. Okay. So if we go back and take a look, way back up here, d is a circle. Okay. It's that circle x squared plus y squared equals 4. Okay, that's again that region projected on the xy axis. So it's going to make it so much easier for us if we switch to polar. Okay, so D is the interior of x squared plus y squared equals 4. Okay, so we would want to do in polar coordinates just r is between 0 and 2, and theta is between 0 and 2 pi. Okay, where x would be r cosine theta and y would be r sine theta. Okay, so we would do the integral. And you don't have to switch to polar. Okay, we can use that if you want. All right, but we're gonna. I would challenge you to try it. Right, try it where x is between negative 2 and 2, and y is between 0 and the square root of 4 minus x squared. And then you have to do it again for y is between 0 and negative square root of 4 minus x squared. It might not end up being that bad. Okay, so I mean, I would challenge you to try it with staying in rectangular. Okay, and I can set that up for you in a second too and just show you what that would look like. We would do the integral from 0 to 2, integral from 0 to 2 pi of negative 4 r squared sine squared theta. Oh, you know what? Oh, you know what I did? Is that z needs to be 5 minus x squared minus y squared. Okay, so we would actually have, if we would have negative 4y squared minus 6y plus 10 minus 2x squared minus 2y squared. So we'd have negative 6y squared minus 6y plus 10 minus 2x squared. Sorry, I forgot. If we're going to do dA, it's got to be like dx dy. So we can't have that z in there. Okay. So we're actually going to have a negative 6 r squared sine squared theta minus 6 r sine theta plus 10 minus 2 r squared cosine squared theta. And then we'd have your r d theta dr. Okay. There we go. Just checking my work here quick. Okay. So we'd have your integral, again, 0 to 2, 0 to 2 pi. And distribute that r. So negative 6 r cubed sine squared theta minus, I'm going to do 2 r cubed cosine squared theta minus 6 r squared sine theta plus 10r dr d theta. Okay. Let's do, you know, I want to get the r's out of there first. So I'm going to switch the order. Since everything's constant, I can do it in whatever order I want. Okay. Okay. So then I'm going to have, when I do this piece, all right, I'm going to have negative 6r to the 4th over 4, so negative 3 halves r to the 4th sine squared theta, minus 2r to the 4th over 4, so minus r to the 4th over 2 cosine squared theta, minus 6r cubed over 3, so minus 2r cubed sine theta, plus 10r squared over 5, or r squared over 2, so 5r squared. So from r equals 0 to r equals 2. Okay, so let's see here. In the first piece, I'll have 16 over 2, so negative 24 sine squared theta, minus, I'll have 8 cosine squared theta, minus 8 sine theta, plus 20. Oh wait, it'll be 16 sine theta. Come on. Don't glitch. Okay, 16. Okay, and I'm actually going to do something here where I'm going to take negative 16 sine squared theta minus 8 sine squared theta minus 8 cosine squared theta minus 16 sine theta plus 20. And the reason I did that is so I could get rid of some here, and I don't have to do two trig identities. When I integrate with the sine squared and the cosine squared, I'll only do it with the sine squared because this is just going to be negative 8. Okay, so I'll have negative 16 sine squared theta minus 16 sine theta plus 12. And I'm going to integrate that from 0 to 2 pi d theta. Okay, so remember sine squared, we 1 minus cosine 2 theta over 2. Okay, so I'm going to have negative 8 minus 8 cosine 2 theta minus 16 sine theta plus 12. Okay, so I'll have, oh, that would be a plus because of the double negative. So I'll have 8 cosine 2 theta minus 16 sine theta plus 4. Now I'm ready to integrate. Okay, so just doing some simplifying up, rather than trying to integrate this right here, we used some trig identities and got down to something a little easier to integrate. Okay, so the integral of cosine 2 theta, we'd have sine 2 theta. If I take the derivative of that, I have cosine 2 theta times 2, so I need a 4 here to give me that 8. Plus 16 cosine theta plus 4 theta from theta equals 0 to theta equals 2 pi. Okay, so I'm going to have 0 plus 16 cosine 2 pi, so plus 16 plus 8 pi minus 0 plus 16. Be careful because a lot of kids see that theta equals 0 and think that they don't have to do anything. Cosine 0 is 1. Okay, and then I end up with 8 pi, which is exactly what I would have wanted to make sure I ended up with before, right? Okay, there you go. Okay. I think we got it then. Yeah, and now that I see that there's a pi in it, I think this integration would have been very tricky. You must be some sort of a trig integral that would have gotten you your pi. Okay. So maybe as a challenge, you can try to do it, leaving it in rectangular coordinates. Okay, and see how far you get with it. But yeah, you'll definitely have some sort of trig integral going on there if you do it. Okay, I'm gonna actually feel free to turn the video off now if you're if you're done. But I'm gonna show you just had we left it. Let's see how far we can get with it. I'll switch colors here so it doesn't blend in too much here. So if we had done the integral from -2 to 2 for the x's and 0 to the square root of 4 minus x squared for your y's of -6y squared minus 6y plus 10 minus 2x squared dy dx. Okay, and then you'd have to do it again, switching that upper bound to be negative. So you get the bottom half of it also. So, I mean, I definitely don't want to get too far with this, but we'd have -6y cubed over 3 minus 6y squared over 2 plus 10y minus 2x squared y. From y equals 0 to y equals the square root of 4 minus x squared. You'd have to go ahead and do that. And then, yeah. Integrate that from -2 to 2 dx. So I'll leave that for you to try if you want to do it as a challenge. But remember, we're supposed to get to 8 pi somehow. So there's got to be something trig going on there. All right. I'm going to leave that for now. And that's it.